Hi, my name is Elizabeth Agoritis. I'm co-organizing this CECAM workshop with Ludovic Vertier, Patrick Charbonneau, and Francesco Zamponi. Our digital meeting will take place next January, but it is in fact a prequel to the physical meeting here at EPFL on recent advances in glasses, which has been postponed to January 2022. In what follows, speakers and participants will tell you more about the workshop and what is the glass problem.
Glasses are everywhere, as you can see the windows, the buildings, and the display on the smartphone. Actually, the glass is one of the oldest materials that humans used, dating back to 6,000 years ago. However, the mechanism of glass formation is still a big mystery even today, in spite of the many theoretical, experimental, and computational studies. To understand the nature of glasses and glass transition, many scientists all over the world have proposed different kind of scenarios and perspectives. However, so far, there is no complete and unified understanding of this subject.
Okay, so I want to talk to you about what it is that excites me about glass. I've worked for a long time with colloids, small particles suspended in a solvent that undergird glass transition just the same as atoms and molecules do. And when I saw this for the first time, working on different aspects of colloid physics, I didn't really understand what the fuss was about. You see, the colloids, well, you push them together and they stop moving. It's obvious. It's like cars on the street in a rush hour. There was nothing remarkable about it, as far as I could see. And yet, the years went by, and little by little, I got sucked in to the excitement that is glass physics. And I think what it is that it's a Kuhnian revolution. It's a scientific revolution in the Kuhnian sense. That is to say, there are different theories that describe the data equally well. And these theories are incompatible with one another. It cannot be that they are both correct. It must be one or the other. And trying to understand, or trying to do the experiments, or collect the data that can distinguish these theories, that we can actually demonstrate which one's right, which one's wrong, that is what I find most exciting about working on glass.
Et pourquoi le désordre est-il important? Laissez-moi de te montrer. Je vais mettre une petite goutte de peinture sur ce disque en plastique. Maintenant, je prends cette plaque transparente et serre la peinture entre les deux disques, comme ça. Le résultat est ordonné et très terne. La peinture se dilate en cercle. Quelle ennui! Mais si j'essaie maintenant de séparer les deux plaques, quelque chose d'extraordinaire se produit. La peinture forme un motif complexe, fascinant et désordonné. C'est le modèle de la nature tout autour de nous. C'est ce que j'aime étudier. Le désordre est différent de l'ordre. Il n'est pas seulement beau, mais permet de créer de nouveaux types de sciences et de matériel.
I will participate to this CECAM Digital meeting on recent advances on the glass problem to be held in January 2021. So in particular, I will have the pleasure to give a talk in the first session of this workshop. So this is a session which is devoted to a problem which is rather long-standing in the field of glasses, which is the problem of the so-called activated dynamics. And it is a session that brings together an experimentalist and theoreticians doing work both with numerical simulations and analytical work on simple theoretical models. So I think it gives a feeling of how complex subjects like this one really need to be attacked from different perspectives in order for progress to be made.
There are many experimental results accessible on supercooled liquids, some of which are still unexplained. For example, during the 1990s, Sid Nagel and his collaborators revealed that the relaxation spectrum of supercooled liquids exhibits a universal shape characterized by power laws. But unfortunately, computer simulations were not able to observe this power law shape. What I like in the glass problem is to use computer tools to address unsolved problems. And recently, new computer methods were developed which allow us to study supercold liquids in experimentally relevant conditions. In the workshop, I will present how these new methods allow us to observe for the first time this power law shape. I'm also really looking forward to learning about the new approaches such as machine learning and how they can be used to study glasses.
And other worthy features that characterize this glassy system in the low temperature regime are the appearance of a new critical transition associated with a fractal landscape and therefore with a hierarchical organization of the minima, the so-called Gardner transition, and also activity dynamic processes that will be part of this workshop, and the presence of strong correction compared to the theory used to describe simple supercool liquids. But on the other hand, from a purely theoretical perspective, the appearance of extremely rough energy and free energy landscapes plays a crucial role, a key role in many different contexts, ranging from biophysics for the modelization of disordered proteins, complex financial markets, and also theoretical ecology.
So one of the problems that I'm really excited about and I'm exploring is the problem of training of disordered materials. Now, by training, I mean something that is a little bit different from design, because in the design approach, you would basically figure out what kind of properties you want your material or your structure to have, and then you build them into the design of that material piece, and then you fabricate it in the lab with those properties later. The idea behind training is that you would start with a very generic structure, a very generic piece of material, and then you put it under certain conditions and let it evolve and basically develop or learn that kind of behavior over time. The idea is that I'm trying to use this principle to basically see how I can, put a certain piece of material under specific conditions over and over for it to develop whatever desired property that I want it to have.
And I'm going to be attending the upcoming CECAM workshop and presenting some of my own work as well. I've been studying the connection between the local structure of particles in glasses and glassy systems and how that relates to their dynamics. And, I'm really looking forward to the upcoming workshop. As a graduate student, one doesn't get too many chances to present one's work, so I'm excited to have the opportunity, especially at a time like this when there haven't been as many meetings. And I'm really looking forward to hearing about what other people are doing.
My PhD project is about the collective dynamics in active matter approaching the active glass transition. I am therefore particularly interested in recent advances on the glass transition to develop my reflections on my own research. Starting a PhD while having to work mostly remotely has been quite tough. These countless weeks of lockdown have kept me from meeting people both in my lab and in other places, while these interactions are determinant to the good progress of my work. It is thus very important for me to have this virtual workshop where I will be able to meet and discuss with researchers from around the world.
I think that a digital meeting will ever be a 100% substitute of meeting in person, but given the circumstances, this is the best way to interact and to keep the community updated. So I'm really looking forward to it. And then, of course, also looking forward to meet again in person at the next second meeting in 2022.